Okay, so when we talk about clock rate, so whenever we talk about rate, we are talking about the speed. Okay, so speed, like in terms of when we are talking about distance and time, we always say that it is nothing but speed. Speed is equal to distance upon time. Okay, so when we talk about rate, we have to divide that particular parameter with time. Okay, so when we talk about this clock rate or the speed, we are actually talking about the clock frequency. It may, sorry. So when we are talking about this clock frequency, we are talking about it measures the number of cycles per second. Okay. So again, one more concept, number of cycles per second. Can you tell me where you have seen this formula before? What is number of cycles per second? Anyone? What is number of cycles per second?
Frequency, sir.
Yes, it is nothing but frequency. Okay, so it is written over here also, clock frequency. So one cycle per second is known as 1 hertz. So 1 million cycles per second is denoted by M hertz or megahertz. And 1 billion is nothing but your gigahertz. So why we are again and again specifying these terms? Because when you try to analyze or when you are looking into the manual of any laptop or any system, you will come across about this particular unit like 300 gigahertz or 700 gigahertz. Okay, so what exactly it is talking about? It is talking about cycles per second. Okay, so when we talk about million or giga, here we are talking about 10 to the power 6 or 10 to the power 9. Okay, so from this very concept, what we'll say that we'll now try to correlate the concept of clock cycle time, which is equal to 1 upon clock speed. Okay, so please don't get confused here. So clock speed or clock frequency, they both are same thing. When we are trying to correlate this with the clock time, it is nothing but reciprocal of the clock speed. So again, this is something like t was 1 upon f. So here we had time and here we had frequency. Now we are trying to analyze this with a clock signal. Okay, same thing we're trying to understand. So how we can correlate these units and data, and how we can solve few problems based on this. Okay, so before going into that, let's take few formulas also. Okay, so if my clock speed is 1 gigahertz, then clock cycle time will be 1 upon 10 to the power 9 hertz. So this is nothing but 10 to the power minus 9 seconds. So here I am talking about this 1 nanoseconds. So one more practical conclusion, what we can conclude from this particular formula, that if I am talking about 1 gigahertz processor, I am talking about the clock cycle time as 1 nanoseconds. Okay, so here the more lesser time you have, or in 1 nanosecond you can it is completing one cycle, so that corresponds to the speed of that particular processor, the higher speed of that particular processor. So everywhere now, when we go and try to understand the logic of a smaller laptops, lesser in size and with a very expensive price. Okay, so that's the most predominant reason behind that is this nanotechnology, or the behavior in terms of the lesser execution time, or the processor is working so fast. In nanoseconds, it can complete a cycle and give you results. Okay, so that means one complete clock cycle period is nothing but 1 nanoseconds. So based on this. Okay, so now we'll derive one small formula and see that how we can calculate the performance. So what about this performance equation? Okay, so let us say that total number of machine instructions be executed in a program P is n. So suppose I have 5 number of instructions that I have to execute, okay, in a program. So steps needed to execute one instruction or cycle per second is S. So here we are taking few variables. Now each step is taking one cycle, one clock cycle to complete. So one instruction will execute in S clock cycles. Is this step is this particular line, is it clear, students? It is saying that steps needed to execute one instruction is equal to S, that is nothing but cycles per instruction. So each step is taking one clock cycle to complete. So one instruction will execute S clock cycle. Okay, so S clock cycles it will take for one particular instruction. So in next step it will be clear. See here. If a clock speed of processor is R hertz, so I know the speed of the processor, then one clock cycle time is 1 by R. We have just seen that my cycle time is reciprocal of clock speed. Okay, so you have to just keep in mind about time is inversely proportional to frequency. Okay, and when we are talking about this speed, or we can see this hertz concept, hertz as unit, so this is my frequency. So 1 by R is nothing but T, which is nothing but clock cycle time. Okay, so then n into S clock cycles will execute in n into S by R. So what is this n? So these are the number of instructions that we want to that we are talking about. Suppose n number of instructions we are trying to execute. Okay, what about this S? This is nothing but the total cycles per second, like steps needed to execute one instruction. So that is nothing but S. So total number of instructions multiplied by cycle per instruction, like how many cycles per instruction we need. So we'll multiply both N and S and we'll divide that particular quantity with the frequency of the processor, and we'll get like how much time it would take, okay, to particularly process or execute in seconds. So unit is in seconds. So based on this, if you look into this part, a computer advertising as having 900 megahertz clock speed R processor does not necessarily provide better performance than 700 megahertz processor, because it may have different value of S. That means the number of steps required to perform these n number of instructions, it can vary. Okay, for example, like with system A, you're doing uh, uh, you have to copy a particular video file from one location to another. Okay, so you're doing this control C and control V. Okay, so this you're doing. Okay, at the same time you're using internet. Okay, you're downloading something. Okay, or at the same time you are watching a movie also. Okay, so these many tasks you are performing when you are using system A, whereas in system B you are doing this control C and control V. For example, this was a 2 GB file, and here you're doing a backup of your files, which is 20 GB. Okay, the same thing, Control C, Control V, and along with music and some of the downloads. Okay, and you are also installing something. Okay, so this S, that is number of steps that is required to complete the n number of tasks. Okay, so there is variation in this particular value of S. So if I'm saying that 900 megahertz is better than 700 megahertz, so it is very important. If we are saying that this is performing in a better way as compared to 700 megahertz, so we have to know this, that they both are doing the same thing. If the nature of task provided to the processor is different, so obviously it will have this different value of S. Okay, so we cannot generalize based on a particular value of megahertz. It depends on the value of S. So again, the S value is nothing but, you can see here, each step is taking one clock cycle to complete. So one instruction will execute S clock cycles. Okay, and what is this S clock cycles? It is cycles per instruction, or steps needed to execute one instruction. So based on this, it will change. It is not directly dependent on the value of your megahertz. Okay. Any doubt? Is it clear, students? I can explain again if it is not. Please tell me if it is clear or not. Hello? Yes or no?
It's clear, sir.
What about others? What about others?
Yes, sir, it's clear.
So let's say that my performance, I'll denote the performance of a particular CPU or processor as P. Okay, and let us denote the execution time as T. So obviously the performance is inversely proportional to the execution time. The more execution time a particular processor will take, lesser is the lesser is the performance of that particular system. So we say, when you say that my system is performing better as compared to yours, so that means it is taking less time for the execution. Okay, so here there is a indirect proportion relation between performance P and the execution time T. So this is first step. When we talk about throughput, we have seen that here we are talking in terms of the server. So number of tasks completed in a unit of time is nothing but throughput. Throughput is directly proportional to the processor performance. So if the number of tasks completed in a unit time is more, that means my performance is also better. So they both are directly proportional to each other. Finally, the third point is nothing but the speed up. So as the name suggests, it is a comparison factor. That means it is a ratio, it is a factor used to compare the performance of two different CPU, okay, or say a X or Y or A or B. So let us assume that the execution time of an instruction in computer is X, is Tx, and for computer Y is Ty. Okay, so execution time is Tx and Ty for system X and Y, obviously. Okay, so we are saying that the execution time for Y system is more than the X. Okay, So obviously the performance of X will be better than Y. Okay. Now, so when we talk about speed up, so it is nothing but performance of X upon performance of Y. Okay, we know that performance is inversely proportional to the execution time. So it will be in the denominator part. Okay, yesterday we saw this. So we can say that after this step, performance of X, I can say that it is nothing but 1 upon Tx. Okay, again divided by, so this is 1 upon Ty. So if we'll do this, so it will be a cross multiplication now. So it is nothing but Ty by Tx. So let us suppose that it is neta. So this is the factor, speed of factor. So whenever we talk about factor, it is nothing but a ratio. Okay, so speed up, you can say that you can divide the performance value or the execution time, which is inversely proportional to the performance of any system, that particular value. So then you can say that performance of X is neta times performance of Y. Okay, so based on this, we'll solve one problem.